Welcome to students. So, today we will be looking into periods of periodic points. In the last class we had seen that we have different kinds of periodic point and what can we predict about the dynamics of these periodic points. Today we shall be looking into what can be the possible periods of this periodic point, like can we guarantee that certain periodic point exists or not. So, let us now look into this example of the circle which we had discussed last time. So, if you take the unit circle, we had considered this map f of theta going to twice theta. So, this is basically the doubling map that we had considered, and in this doubling map we had seen that this has periodic points of all periods, right, because given any k in n, we could find a point P, right. So, basically we are looking into f k theta which is equal to 2 to the power k theta, and if this happens to be equal to theta, we found out that theta comprise something like 2 m pi, right, upon 2 to the power k minus 1, and these points exist for every k. So, this has periodic points. So, I should say that there exist periodic points of all periods k. Similarly, if for the same x, right, if we change our x is same S1 and we are looking into the irrational rotation. So, if we look into the irrational rotation, then we could easily see that this does not have any periodic point for any period, right. So, if I want to look into what are all the possible periods of periodic point, well, there are no possible periods of periodic point. That possible period set happens to be an empty set. But in the same case, when I look into x equal to S1 and now I am looking into the rational rotation, then we find that we are now looking into rational rotation. So, our rotation, the angle of rotation happens to be a rational multiple of 2 pi, and depending on what that rational is, we always get an n such that every x in x is a periodic point of period n. We have a fixed n here, we do not have any other periodic points, we just have one particular period here, that is n, and all points here happens to be periodic with period n. Now, let us look into some more examples here. So, I would like to go into this drawing here. So, we have this f x equal to minus x. Now, if we try to analyze this graph f x equal to minus x, we find that this particular point 0 happens to be a fixed point, it is a point of period 1, and if we look into all other periods, right. So, if you look into all other points, so all other points happen to be periodic points of period 2. So, f x equal to minus x has periodic points of period 2 and periodic point of period 1. So, there is only one periodic point of period 1. On the other hand, if I look into this graph of f x equal to x square, so if I consider the dynamics of x square, we find that it has two fixed points here, a fixed point at 0 and a fixed point at 1. Now, we have already discussed these examples earlier. So, it has a fixed point at 0 and a fixed point at 1, and what we find is that does it have periodic point of other periods. So, if we try to analyze that, maybe we can think of looking into the graph of f composite with f, that would take x to the power 4. But if it takes x to the power 4, we find that this graph is again going to be something drawn along the dotted lines, and if we see this particular graph, right, then the only place where it intersects the diagonal is 0 and 1, and we very well know that the fixed points for f square are also the fixed point, f square x equal to x are also the fixed points for f, right. So, basically they have the solution of f x equal to x is contained in the solution of f square x equal to x. So, we find that these are the only 2 points where it intersects. So, there is no possibility of a period 2 point here. What happens again if we try to look into f cube, right? Again we would find something going along the dotted lines, right. We will find something going along the dotted lines here. So, again here we find that this will not have periodic point of period 3. The only periodic points are periodic point of period 1, and 0 and 1 are the only 2 periodic points. So, what happens in case of f x equal to sin x now? Now, a very simple graph of sin x, right. We know that sin x is always less than or equal to x here, right. And if we try to see what happens to sin of sin x equal to x, supposing we want to look into this part. So, here we have sin x equal to x has only one solution, right, that is x equal to 0. Now, we try to see if it has periodic points of period 2. So, if to look into whether it has periodic points of period 2, we look into whether sin of sin x equal to x has some non-trivial solution. But sin of sin x equal to x, since I know that sin x equal to x has only one solution, x equal to 0. So, sin of sin x equal to x will also have only one solution, and that solution is sin of x equal to 0. But we know that we are now looking out for periodic points in that case, and sin x equal to 0 happens into all say even multiples of 2 pi, and in this case we can say that the only solution can be x equal to 0. So, we find here that if my function is sin x, and if I am looking into the dynamics of the function sin x, again I have only one periodic point of period 1, right. So, period 1 is the only possibility, right. We do not have periodic points of any other periods. So, in general, could we really claim something about the period of periodic points? Can we say that certain periods will occur and certain periods will not occur? So, a surprising result to that is something called Sarkowski's theorem. So, I will look into what is Sarkowski's theorem just now. This was a surprising work done by Sarkowski's in 1964. In fact, this result came to be known to the rest of the world only after 1975. So, because this was published in a Russian journal, and during those days, you know, whatever research Russia did was used to be kept very confidential. So, not many knew about this result, and then suddenly after 1975 people tried to know, or people came to know about this particular result. Now, what is Sarkowski's theorem? So, this was proved in 1964 by Alexander Sarkowski. He is a Ukrainian mathematician, and I think he is still doing some kind of dynamical work here. Dynamical system, he is still working with some kind of stuff. So, you start with say f going from R to R. Now, we are looking into interval maps. So, if f is continuous on the interval and we consider the following ordering of natural numbers. So, we know that 3, now how do we order the natural numbers? So, I am considering 3 to be the greatest, the largest number here. So, now we are ordering natural numbers, 3 is the biggest one, then 5 is less than 3, 7 is less than 5, and like that we are exhausting all the odd numbers here. The next comes up, what comes in the next order? So, once we have exhausted all the odd numbers, the next comes into 2 multiplied by 3, right, followed by 2 multiplied by 5, followed by 2 multiplied by 7, and so now what we are exhausting is, we are exhausting 2 multiplied by all odd numbers. What now remains is 4 multiplied by 3. So, next is 4 multiplied by 3, 4 multiplied by 5, 4 multiplied by 7, and so on till we have exhausted the multiple of 4 with all odd numbers, and we proceed like that we come up to say 2 to the power k multiplied by 3, followed by 2 to the power k multiplied by 5, followed by 2 to the power k multiplied by 7, and in that way we exhaust all multiples of odds with 2 to the power k, and we continue this process, and in continuing this process we later on end up what remains is only the powers of 2, because all multiples of odd numbers are exhausted, right, all that remains is powers of 2. So, we look into the powers of 2 and then we order the powers of 2 again now in a decreasing order. So, your 2 cube is followed by 2 square, is followed by 2, is followed by 1. So, this is a different kind of ordering of the natural numbers. This is not the usual ordering that we take up. This is a different kind of ordering of natural numbers, and we find that in this particular ordering 3 is the largest number and the smallest number is 1, and in fact 4 is much less than 3, right. So, this is the ordering of natural numbers, and what Sarkowski's proved was a really wonderful idea. It is something astonishing that if f has a periodic point of period k and k precedes L in this ordering, then f will also have a periodic point of period L. So, that means supposing now in any map from reals to reals, if I can find that there exists a periodic point say of period 4 into 7, then I will have periodic points of all these periods, all these numbers which follow 4 into 7, there will be all these periods coming up, and then what we find here is maybe we may not find a periodic point of period 4 into 5, maybe we may not find a periodic point of 4 into 3, but we are guaranteed that all these periodic points will occur. So, this is really something really unique, and it is unique about the interval maps only because we are looking into the interval maps. Basically, when you look into the real line, it is a continuum and it is basically an ordered set. So, it is an ordered continuum, we are just using the property of an ordered continuum. So, this result holds only for real line, but still this gives us a very nice property of the dynamics of real numbers. So, this property of dynamics, look into a periodic point, you can guess what are all the periodic points that would exist. What we shall try to see here is proof of Sarkowski's theorem is a little bit involved. It would take me again one more lecture to prove the Sarkowski's theorem. It is not too difficult to understand, but we will not be doing we will not be doing the proof of Sarkowski's theorem. There are many places where now you can find out, like if you just search on the web, you can find out many different proofs of Sarkowski's theorem, and you will find that each author claims that he has a better proof of Sarkowski's theorem. So, you can look into any of the sources to look into the proof of Sarkowski's theorem. What we shall discuss now is what is the converse part. Now, what do we mean by a converse part? As I said is that we know that if I have a continuous map, then for this continuous map we can say that you have, if a periodic point of period k exists and if L is following k in this ordering, then f will also have a periodic point of period L. The converse to Sarkowski's theorem is something very different. It says that if you fix an L, can you say that if L is following k, then you have a periodic point of you have a function f such that it has a periodic point of period L, but it does not have a periodic point of period k. So, this is what is known as the converse of Sarkowski's theorem, and we will be discussing a few examples here. So, we look what happens conversely. Now, I am just looking into one simple case. Say my function f is going from the interval 1 5 to the interval 1 5, and f has a periodic point of period 5. We are just going to show that it has no periodic point of period 3. So, let me take this particular function. Now, we define this function in such a way that f of 1 is 3, f of 3 is 4, f of 4 is 2, f of 2 is 5, f of 5 is 1, and in between it is all linear. So, the function is linear in between, it is a straight line in between, the graph is a straight line in between. So, it is a linear function in between, but this gives me now 1, 3, 4, 2, 5 gives me a periodic orbit of period 5. So, now we have this periodic orbit of period 5, we want to find out what happens, does it have, we want to show that actually it has no periodic point of period 3. Now, remember in Sarkowski's ordering 3 precedes 5, right. So, if I have a periodic point of period 5, it implies that I should have periodic point of all other periods, but I cannot guarantee about 3, and that is what this example shows us, that this particular thing, this particular function has a periodic point of period 5, and we will prove that it has no periodic point of period 3. So, now look into this fact, I am looking into here. So, let me look into what happens here. So, when I see f of, say I am looking into what happens to f of 3 4, then f of 3 4 is 2 4. Let us go back to our real analysis, right, and let us try to look into the intermediate value theorem. We just recall the intermediate value theorem, which says that if I am looking into a continuous map on an interval, and if for my interval I, if f of I is containing I, right, then f has a fixed point in I, right, then f has a fixed point in I. Then f has a fixed point in I. So, now if I am looking into this particular function, f of 3 4 happens to be equal to 2 4, right. So, f has definitely a fixed point in basically in 3 4. So, there will be some x in 3 4 such that f of x is also equal to x. Now, we want to look into, we just want to show that it has no periodic points of period 3. So, we try to look into what happens to f cube. So, now we are just iterating this graph, right, we are just iterating f cube, and what we find is that what is f cube of 1 2. So, if I look into 1 2, right, we basically find that this interval 1 2 is mapped into the interval 3 5, right. So, under 1 f it is mapped to 3 5, where is 3 5 mapped to? So, if I look into 3 5, right, so this 3 5 is basically mapped into 2 5, right. So, under f 3 5 is mapped, sorry, 3 5 is mapped into 1 1 4, right, 3 5 is mapped into 1 4, and where is 1 4 mapped into? So, I find that 1 4 is mapped into 2 5, right. So, under f cube my 1 2 is mapped into 2 5. Similarly, if I look into my f cube of 2 3, now I am looking into, now I know that where is this interval, so I am looking into this interval. So, this interval is basically mapped into 2 5, right. So, 1 2 is mapped into 2 5. Now, let me look what happens to 2 3. So, if I look into this particular interval 2 3, right, where is 2 3 mapped to? So, in the very first instant, right, I can say that my 2 3 will be mapped into, right, my 2 3 is mapped into this part 4 5, right. So, 2 3 is mapped into 4 5, where is 4 5 mapped into? So, 4 5 is mapped into 1 2, right, and where is 1 2 mapped into? So, if I look into 1 2, it is mapped into 3 5, right. So, under f cube 2 3 is mapped into 3 5, right. Now, what happens to, now I am not considering 3 4, let us look into what happens to 4 5. So, under f 4 5 is mapped into 1 2, right, 1 2 is mapped into 3 5, and where is 3 5 mapped into? It is mapped into 1 4, right. So, under f cube 4 5 is mapped into 1 4. That means, if I look into these things, right, there is no x in 1, 2 for which f cube x could be equal to x, because these two are disjoint, right. The only place where they are intersecting is 2, but 2 happens to be a periodic point of period 5, right. Similarly, if I look into the interval 2, 3, right, there is no point in 2, 3 for which f cube x could be equal to x, because 2, 3 is mapped under f cube to 3, 5, right. The only point of intersection is 3, which is a periodic point of period 5. And similarly 4, 5 is mapped under f cube to 1, 2. So, if I look into 4, 5, right, then we find that this again this does not intersect this, the only place it intersects is 4, which is a periodic point of period 5. So, there is no place where f cube could have mapped, could take this particular interval. So, there is no x here which could be a periodic point of period 3. So, that means there is no periodic point of period 3 in these 3 intervals. Now, what happens to the interval 3, 4? So, let us look into 3, 4. We know that where is 3, 4 being mapped to. So, 3, 4 under f, right, where is it mapped to? So, it is mapped to 2, 4. Where is 2, 4 being mapped to under f? 2, 5. 2, 5. And where is 2, 5 being mapped to under f? It is a map to 1, 5. So, what we have is that f cube maps 3, 4 to 1, 5. Now, since it maps 3, 4 to 1, 5, I have this intermediate value theorem which says that if f cube of I is containing I, right, then there exists a fixed point here. So, now we have that f cube of 3, 4, right, is mapping into, so this should contain a fixed point of, it should contain a fixed point for f cube. If I again look into this case, right, my f of 3, 4 happens to be 2, 4. So, I am looking into this case, f of 3, 4 happens to be equal to 2, 4, right. Since this happens to be 2, 4, I have f of 3, 4, f of I also containing I. So, that means that f should also have a fixed point in 3, 4. Now, so f has a fixed point in 3, 4. Now, we want to say that since f has a fixed point in 3, 4, we have f cube also has a fixed point in 3, 4, right. We only want to claim that both x and f cube x, both f x and f cube x will have the same fixed point in 3, 4. So, already there is a fixed point of period 1 here, right, and I can simply draw that part, right. So, I find that this is a fixed point here. So, already I know that f has a fixed point here. I want to claim that f cube also has a fixed point, and that fixed point is same as this fixed point as the fixed point of f, right, and so there is no periodic point of period 3. Now, what we judge here is that f of 3 by 4 is mapping to 2, 4. Now, when I look into 3, 4, right, it is mapping to 2, 4, right. So, my f is decreasing in this interval, right. So, the function f here is decreasing in this interval. Again, f of 2, 4 is mapped to 2, 5. So, if I look into f of 2, 4, so I am looking into this whole interval, right, in f of 2, 4 is mapped to 2, 5, right. So, what it is mapped to? It is mapped to 2, 5, but again in this interval the function is completely decreasing. So, the function is decreasing in this interval also, and then f of 2, 5 is mapped to 1, 5. So, if I again look into 2, 5, right, it is mapped to 1, 5, but again the function is decreasing in this interval. Now, you have a monotonically decreasing function, right. Your function here happens to be, so if I look into f cube on 2, 3, 4, right, it is basically a monotonically decreasing function. Since it is monotonically decreasing function, it will basically cut the diagonal only at one point, or in other hands, this if f cube has a fixed point, right, basically that fixed point will be same as the fixed point of f x. So, f x, so this f cube, right, since it is monotonically decreasing here, this f cube has just one fixed point here, and that fixed point is basically the fixed point of f. So, there is no periodic point of period 3, right. So, all we can conclude here is that f has no periodic points of period 3. I hope this is clear. So, let us try to look into another example here. Let me try to push this up, let me try to look into another example here. So, I take this example. So, my f is from 1 4 to 1 4 and we find that it has a periodic point of period 4, but it has no periodic point of period 8. So, I am just trying to draw this particular stuff. So, f1 is 4. So, I am looking into f1 to be equal to 4, f4 is 2. So, f4 is 2 here, right, f2 is 3 and f3 is 1. Now, this has a periodic point of period 4, we know that very well, but again you can use similar methods to show that it will not have a periodic point of period 8, right. All you need to see is that the function happens to be completely decreasing, it is monotonically decreasing in this interval 1 3, right, and hence it will not have a periodic point of period 3. The only fixed point, the fixed of period 8, the fixed point here is basically this particular point which lies here, right. You can think of, we will have a periodic point of period 2. So, you can find that somewhere over here there will be a periodic point of period 2, right, but it will not have any periodic point of period 8. So, the only periods that this f admits are 1, 2 and 4. So, it does not have any other periodic point. So, the periods of f here in this case are only 1, 2 and 4. And now we go back to our Sarkowski's ordering, right. In our Sarkowski's ordering, what happens to the end of the order is the powers of 2, right. So, now the number, the natural number that preceded 4 was 8, right. Since it does not have a periodic point of period 8, right, we can think it will not have a periodic point of any other period. We have not proved Sarkowski's theorem, but it is a proved theorem, right. So, it definitely holds. So, here we find that this will have no periodic point of any other period. So, the only possible periods of f are 1, 2 and 4. So, this case turns out to be really interesting case and we would be interested in looking into further. At least we should be able to prove some part of it, and that is what we are going to prove here. Now, this is a surprising change of, as I said, that in 64 when Sarkowski's proved that there is no period, that there is a Sarkowski's ordering and all continuous interval maps basically satisfy the Sarkowski's ordering in terms of periods. This result was not known because it was published in a Russian journal, nobody used to read Russian journal and most of the research in Russia used to be kept confidential. So, in 1975 when the first definition, of course, this is very historically very important because this was when the first definition of chaos was given. So, in 1975 there were two mathematicians at University of Maryland. So, they gave this definition, they gave the first mathematical definition of chaos and they proved something which can be called a corollary to Sarkowski's theorem, and their proof is very independent because they did not know about Sarkowski's theorem. It was only after this paper came up and then people realized that, oh, this is a very simple affair and it is such an interesting affair, that then Sarkowski's theorem was known. So, we come back to now 75 and we come back to what is basically, this was a theorem by Lee and York, but we now as of now we understand it to be a corollary to Sarkowski's theorem. So, we shall look into this corollary to Sarkowski's theorem. This was proved by Lee and York, and this corollary says that if my function f from R to R is continuous and suppose f has a periodic point of period 3, then f should have a periodic point of all other periods. this was proved by, in fact, as I said that this was the first paper, or this was the first instant of a mathematical definition of chaos. We will definitely go into this paper further, because we want to get into the mathematical definition of chaos, but we will first look into the proof of this corollary. Right. So, simply we want to say that if a function f has a periodic point of period 3, then it has a periodic point of all other periods. So, how are we going to prove this particular theorem? So, we start with, say, I have drawn this figure here earlier. So, what we have here is that I have 3 points A, B and C, f of A is equal to B, f of B is equal to C and f of C is equal to A, and I have this condition that A is less than B is less than C. I am just looking into a periodic point of period 3. So, I am just looking into a period 3 orbit here. So, period 3 orbit I could have had taken the other way around also. Say my f of A would have been equal to C, right. Then my f of B would have been equal to, f of C would have been equal to B, right, and then f of B would have been equal to A, right. We could have had the other way around also, but if you try to look into what happens in the other way around, so supposing I had a C here, right, then f of C would have been equal to B here, and then f of B would have been equal to A here. Supposing I have this particular kind of ordering here, then in that case also what I would have had is the same figure, in fact the mirror image of the same figure, right? No difference here, it would just have been a mirror image of the same figure, right. So, what we are trying to see, so the other case vacuously follows from this particular case, right. The proof would be identical here even if you look into the other case, and hence we will try to prove it with this particular specific case that A is less than B less than C, f of A is B, f of B is C and f of C is equal to A. So, we look into this particular specific case and we try to prove this particular corollary or this particular Leoch's theorem, right, in terms of this condition. So, let us now look back to the into the proof. We will come back to this figure once again, but let us look into this proof. Now, what are ideally we going to use? So, we are only going to use intermediate value theorem for this proof and nothing else. And as I had said earlier also, right, let us start with this proof. So, we know that we have this intermediate value theorem, which says that if f of I contains I, then there exists x belongs to I such that f of x equal to x, right. We are just using this part, and now we will see how are we going to utilize this concept over here. Now, what happens here is, let me look into this graph once again. So, we have this graph once again. Now, I am only concentrating on 2 intervals now. Now, this function is from real line to real line. So, it is basically an infinite, R is basically sort of an infinite interval, but we will concentrate only on 2 intervals. So, I am calling this interval as I0 and I am calling this interval as I1. So, I have this interval I0, I have this interval I1. Now, what happens to I0 and what happens to I1? So, we know that, so let I0 be equal to this interval AB and I1 be equal to this interval BC. Now, what happens to I0? So, what is f of I0? So, this is basically BC, right, which is equal to I1. So, f of I0 is I1, right, but what is f of I1? So, this is like BC, right. Now, B is mapped to C, C is mapped to A, right. So, this is basically going to be my interval AB, right, which is basically nothing but it is I0 union I1. It is AC, and this is I naught union I1. Now, we have this. So, now what we have is that f of I1 contains I1. So, here my f of I1 contains I1. In fact, I1 is a proper subset of f of I1, right. So, let me call this I1 to be this interval. Now, I am looking into all intervals in terms of j's, right. So, let me call this as my initial interval j naught, right. So, this is my initial interval j naught, and we know that f of I1 contains I1. So, what we try to do is, since f of I1 contains j naught, right, then that means that my I1 will have a subset, proper subset, a proper interval or proper subinterval of I1 such that its image will be the whole of I1, right. I am just looking into the property of interval, property of the continuous function, which will take intervals to interval, right. So, there exists an interval j1 which is basically a subset of j naught, right, such that f of j1 is equal to j naught. So, now I am looking into this part over here. So, let me look into this phase here. So, this is basically my bigger one, this is basically my j naught, right, and within j naught I get some subset here. I do not want to draw that part exactly, but I just want to say that I have a subset here, right. So, j1 such that j1 is a subset of j naught, but f of j1 is equal to j naught. Now, we look into this j1 further. Now, think of what happens to f of j1, right. So, f of j1 is j naught. So, what happens to f square of j1? This is again f of j naught, which will again be containing j naught. So, this is again going to contain j naught. So, if I start with my j1, I apply f to it 2 times successively, I find that that contains j naught. If it contains j naught, it also contains j1. Since it also contains j1, that means that I should have a subset j2 of j1, right. So, basically there exists a subset, a subinterval j2, and now this is not an ordinary subset, I am looking into it in terms of interval. So, I get a subinterval j2 contained in j1 such that if I look into f of j2, f square of j2, right, that will basically be containing j naught. And I can say that this basically, maybe I can say that this f of j2, right, will be equal to j1, right, and hence f square of j2 will contain j naught, right. We can think of it in this particular term. So, iteratively we are looking into this aspect. So, if I continue in this manner, what happens if I continue in this manner? So, continuing, what are we trying to do? We are trying to prove a periodic point of all periods, right. So, we get a jn minus 2, right, which is basically a subset of jn minus 1, which is again basically a subset of, sorry, it is jn minus 3, it is basically a subset of j2, subset of j1, subset of j naught, right, such that f to the power n minus 2 of jn minus 2, right, contains j naught. Now, here we are having this for some n right, we We can iteratively do this for all possible n's. Now, let me look back into this figure once again, right. Now, this is possible for what kind of n's? Let us try to see here. So, let us look into this figure once again. Now, let us look into this part, right. So, what we find here is that f of I1 contains I1, right. Since f of I1 contains I1, there is a periodic point, there is a fixed point of f, right, contained in I1, and in fact one can easily see in this graph that this is the fixed point here. So, f definitely has a fixed point in I1. What happens to, say, when n equal to 2? What happens in that case? So, we go back here, right. We look into this aspect, we are looking into the fact here that we can make such kind of a continuation, just observation that we can make such kind of continuation, right, for some m in n. And now, let us go back to what happens for n equal to 1. So, we see that for n equal to 1, right, since my f of I1 contains I1, right, there exists x belonging to I1 such that f of x equal to x. So, there is a fixed point, period 1 point contained in I1. Now, for n equal to 2, what happens in that case? Now, let us look into this fact that f of I naught, right, contains I1. So, what happens to f square I naught? In fact, f of I naught is completely equal to I1. So, what happens to f square I naught? So, that will contain f of I1, right, and what happens to I1, f of I1? It contains both I naught and I1, right. So, I can simply say that this contains I naught. Now, my f square of I naught contains I naught, that means that f square has a fixed point in I naught. So, that means there exists y belonging to I naught, right, such that f square y is equal to y. But then this y cannot be a periodic point of period 1, this y cannot be a periodic point of period 1, since f of I naught, right, is basically I1, right. So, this y, because this y belongs to I naught, this y cannot be a periodic point of period 1, and hence this y has to be a periodic point of period 2, right. So, this y is a periodic point Now, we know that y is a periodic point of period 2. So, we have proved the existence of a periodic point of period 1, right, a periodic point of period 2, period 3 is already given to us, right. So, now we can assume that let n be greater than 3 and we will produce a periodic point of period 3 of period n, a periodic point of period n. Now, we already know that we are getting this intervals. So, we will look into what we had done already. So, we have already discussed this part that we get this intervals Jn minus 2, right, contained in Jn minus 3, right, contained in J2, right, contained in J1, contained in J naught, which is equal to my I1, right, such that my f to the power n minus 2 of Jn minus 2 contains J naught, right. We know that part very clearly. Now, let me look into this fact. Since this contains J naught, right, I can find now what is f of J naught. F of J naught contains I naught also. So, I can find an interval. So, there exists J n minus 1, right, a subinterval of Jn minus 2, right, such that f of Fn minus 1, right, of Jn minus 1, this will contain I naught. So, what we tried to do was, now we are trying to, this is simple iteration what we did, right. Now, I am coming back to the figure again, let us try to look into this part. The simple iteration was, we started from here, we started going into subintervals here, every time we stayed here, right. At the n minus 1th stage we are just moving here, right, because again this is being mapped here also. So, n minus 1th stage we are moving here, right, and then what happens here, we are now again in the nth stage, we are again, we know that the image of this particular interval is here. So, the nth stage we are again going back here, right. So, what we have here is Fn minus 1 Jn minus 1 contains I naught, and so I can say that f of n of Jn minus 1, right, will be containing I1 which is equal to J naught, and in fact my J naught also contains Jn minus 1, right, my J naught also contains Jn minus 1. So, for Fn, right, I find an interval Jn minus 1 such that Jn minus 1, f of Fn of Jn minus 1 is containing Jn minus 1, and so there exists a point P, right. So, there exists P, or maybe let me push up in the next page, there exists P belonging to Jn minus 1 such that Fn of P is equal to P. Is this P a periodic point of period n? We said that our n is any number greater than 3, but what we observe is that if I start with P, my P belongs to Jn minus 1. So, it is basically a point of I1, right. So, my P, my Fp, right, up to Fn minus 2 of P, right, this was all belonging to I1, but my Fn minus 1 of P was in I naught, and then again my Fnp is equal to P. So, that means that this P, this point P, since this point P satisfies Fnp equal to P, right, this cannot be a periodic point of a period less than n, because if this was a periodic point of period less than n, then the entire orbit would have been only in I1, right, it would not have jumped to I naught, right, the entire orbit would have been just in I1, but it jumps to I naught, right, and then comes back again to I1, and hence we can say that P is a periodic point of period n, and so we are proving the existence of a periodic point of period n for all possible n, right. So, for all natural numbers periodic point exists, and what we have proved is, we have basically proved Lie-Hock's theorem, or what one can say is the corollary to Sarkovsky's theorem. So, I push this again here what we have proved here, and we end the lecture today.